All right. So let's keep kicking here. And I probably won't go super long today. I just want to kind of finish up some of the stuff we're talking about. I think we got a good amount of the background information covered, but we'll see how things go. Hopefully everybody survived the ice storm.
Yes, sir.
Let's go here. Okay, so last time we were talking about DNS. So the idea of when we type in www.google.com, what actually happens? There is some sort of lookup. There's a mapping that exists on the internet that maps between domain names, i.e. something as easy for human beings to remember, like google.com, and actual IP addresses, the things that are what actually uniquely identifies a computer on the internet or on any sort of network. But if we're talking about routable IPs, we're talking about uniquely identifying it on the internet. So at the end of the day, using TCP/IP, over the internet requires that we ultimately have our browser. So typically when we're typing in www.google.com, we're doing that inside of our web browser. So we would do www.google.com here and press enter. So this web browser is a client of the internet. So specifically it's an HTTP client. And we'll talk more about that and the use of HTTP and for some other things. But when we press enter here, we are asking our browser to connect to another computer. Typing this in right here does not give us enough information to know which computer we're connecting to. This is a domain name. The google.com part is called a domain name. And www is a computer at, it's called an A name, is a computer at that domain name. So you could have the same computer hosting multiple A names. It could be at the same IP address, or Google's kind of the other direction. They probably have lots of computers that are serving their web service. But in any case, when we type this in, we are asking something to turn this into an IP address so we can directly access Google's computer given its IP address. That way, as users of the internet, we don't have to memorize a whole bunch of IP addresses. Just like with our cell phones, we're not, we don't have to memorize a whole bunch of phone numbers. Now, we just say, call mom or something like that, and the phone remembers who mom is and maps it to the actual phone number and dials that number. Okay, so this is something we're already used to using. Now, this is a hierarchical approach. So typically, like for instance, if we use Concordia as an example, when I type in www.google.com, I'm currently connected to Concordia's network. So Concordia is going to run its own DNS servers. And the DNS servers at Concordia are going to be a collection of internet addresses that let's say, are commonly visited here on campus. And we're not just talking about 5 or 10 addresses. It's going to hold a collection of probably thousands of domain names with the corresponding IP addresses. But it won't necessarily be a complete list of all DNS and all domain name to IP address mappings. So what would happen is if I typed in Google www.bob.com, it probably actually exists. So let's try to make a guess at something. www. Just going to bang on the keys.com. All right, says this site can't be reached. So I'm going to make a guess here that this domain name does not actually exist. All right, so what happened here? Well, first it sent the request to Concordia's DNS server. Concordia's DNS server then said, okay, well, I can't find that, but let me ask the DNS server that I report to, okay, that I have a trickle effect with. So I'm going to pass you off to them and say, hey, have you heard of this? If so, give me the IP address. Well, that DNS server is going to look and say, oh, I can't find it. So I'm going to pass it up another level, so on and so forth until it finally gets to the top level. We mentioned last time that there's these main DNS hubs around the world that are meant to be the kind of the storehouse of all domain names and mapping to the IP addresses. But you imagine that if every single computer hit those hubs directly to do all lookups, given the number of people that are using the internet at once, that would become kind of problematic. Now we're back to, bandwidth and the number of people connecting at one time, putting people on hold, things like that. And that would slow the internet way down. That's why we've distributed our DNS service across the internet and had more local lookup partners that can pass the buck if they don't have the answer. That way we're filtering who actually gets to that top level. So with that in mind, is my internet down? So this is kind of an interesting thing as for a consumer. When you, and this isn't always the case, but this is something to try. If you maybe go and look up, here, let's just do DNS lookup. And we'll do www.google.com here. All right, so here is the A record for www.google.com. The actual domain name is google.com. www is, I would usually think of it as like a machine at that domain, but it's actually a mapping because it doesn't necessarily have to be a specific machine. Okay, but in any case, I have the IP address of Google here. So if I were to come up here and I would just to type that IP address in, it'll take me to Google's website. Okay. So what I might do if I were you is write down that IP address on a little piece of paper and put it in a drawer somewhere, because presumably if you you can put it in the notes on your phone too, as long as it's local. Don't send it to yourself in an email because you might not be able to access it if your internet's down. But if you think your internet might be down, the first thing to try right off the bat is to just type in the IP address instead of google.com and press enter. If that gets you to the website, the correct website, what that actually tells you is that your internet service provider's DNS server is down. So it's not resolving IP domain names for you, and it's also not passing the buck. So it's not that your internet's not working, it's that your DNS that you're connected to is not working. So your lookups aren't happening. So now you have to use direct IP addresses if you want your internet to work. Now, obviously, you're probably not going to have the list of all IP addresses you might ever want to go to, but at least that, at least that tells you whether or not this is a problem that your internet service provider needs to send trucks out to start fixing things on wires leading to houses, as opposed to fixing something that is internal to their network. All right, so kind of a common thing that can happen with I'm going to say check DNS first. Try Google. Let's see, we'll say try www.google.com IP first. That's that guy. If it gets you to the site, your internet is fine. Your DNS, let's call it your ISP's DNS, Internet Service Provider, is ISP, is down. Okay, so kind of an interesting thing to consider on the internet, is that is somewhat of a common thing that happens. Looks like you wrote that twice. Okay, so actually, before I get to that, I want to talk about this. Any questions on DNS and its role? All right, so again, we really want to think about the internet as this giant network. It's a network of networks where we have clients of that network, like you or me most of the time. And then we have servers of data on that network, like Google's web server. So Google's web server hands out pages, and it also, there's a service behind that, that is the Google search engine. That's providing a service, and we're going to talk about that with HTTP here in a few minutes. Now, we do have something called QoS. Does anybody know what that means?
Quality of service.
Quality of service. All right, so QoS stands for quality of service. And this is the idea of policing, we're going to say, a network. In this particular context, this is what QoS means. The idea of policing a network to ensure the most, I'm going to say, that acceptable use is a priority over less important use applications. All right, we talked about this some with like BitTorrent, because this has been, especially in the early days of BitTorrent, this was a problem on a lot of university campuses. What would happen is people would, all these students were using BitTorrent on the network, which was using up a lot of bandwidth on the network. And again, we don't have infinite amounts of bandwidth, and back then we had even less bandwidth than we have today. But regardless, whoever you're, wherever you're at, your apartment building, your ISP, your, the university here, they don't have unlimited amounts of bandwidth. So if we had 500 students all running BitTorrent at the same time, that would take up a lot of the university's bandwidth, which would then make the other applications on campus, email, the web server, things like that, the system for registering for classes, that kind of stuff. It would make those things become so slow or unresponsive that the average the applications that we might use on a daily basis on campus were no longer functional. All right, so that's a problem with a network. So if you're a network administrator, you want to make sure that you think about, what is the purpose of my network, and how do I ensure that the users who are using my network for its desired purpose are getting a good quality of service, while the people who are trying to use it for less important purposes or even malicious purposes are either getting no service or significantly, a lot of times we call it throttled. So we might say we're going to throttle the bandwidth to applications that are deemed less important to keep available the bandwidth to support the more important applications. And you probably see this with your data plan on your cell phones as well. You know, you might have, like, for instance, my phone, my data plan, I have unlimited data on my phone. So it says you have unlimited data, but we may throttle your bandwidth, slow down your data connection once you've downloaded so much data in a month, for example. So what they're trying to keep me from doing is trying to keep me from abusing my data plan, you know, running, you know, we'll just keep using the same example, running BitTorrent or something like that off my data plan, which is going to be using up a lot of the network bandwidth, relatively speaking. So it's trying to keep me from doing that, because when it throttles my internet, when it slows it down, chances are I'm still going to be functional. I'll still be able to go to web pages. I'll still be able to check email. I just maybe wouldn't be able to do large downloads at as fast of a rate because of that. Similarly, again, we're not in a situation where we have unlimited bandwidth. So if I'm in a really busy city, you know, even if we have, you know, this is kind of the thing with like our 5G networks today, we try to consider the bigger the number of the network we're on, the 5G is better than 4G and those kind of things. A lot of times, some of those technologies deal with your ability to get a signal, to make a phone call, things like that. They don't necessarily translate directly to a speed. They may translate directly to a capability of bandwidth, like the amount of maximum data that can flow over that network. But it doesn't necessarily speak to how much data is actually available. All right. You could certainly serve a 5G network, a 5G wireless network through a dial-up modem. I'm sure that isn't really done, but you could. So now you have, you know, 3 kilobytes per second of, you know, we talked about the 33.3 kilobits per second, or 56K kilobits per second of data. We can certainly operate off of that. We can certainly serve a 5G network with that. So when we say 5G network, what we're really talking about is a local area network or a municipal area network, local as far as the tower goes. So when your phone connects to a tower, that's kind of like you're connecting to a router. And that router is handing you out an IP address on that network. And as you move from tower to tower, the towers are passing you off to each other to continue to provide you service. All right. So you're kind of part of a moving network, if you will. You're jumping from a local area network to local area network as your phone changes in geographic location. But that service provider might say, hey, we have a lot of people, take like a Chicago or something like that, where, you know, during the work week in downtown Chicago, that's going to be a pretty congested area with lots and lots and lots of people all connected on the cellular network at the same time. You are probably going to have moments where the congestion is so bad that they have employed some strategies, some QoS strategies to take the major use of the data networks, of the cellular networks, put them at a higher priority than the less important uses. So maybe phone calls and text messages continue to work, yet HTTP web-based data is throttled. Something along those lines. So with you know, that in mind, this idea of QoS is around us all the time. And we kind of play victim to it because we don't have any control over it. And a lot of times the idea would be that we don't notice, because most of our applications we use on the internet, we don't necessarily measure in terms of speed. We talked about that earlier in the course when we said, well, how fast of an internet connection do you actually use? Most of the stuff that we do doesn't require huge amounts of bandwidth. Just that it just requires an amount of bandwidth available. So the hope is that even though we are probably victims of QoS relatively often, we don't really notice unless we try to do something that is very measurable. You're only really measuring your internet speed when you are trying to download something and want to know how long it's going to take. You know, you don't check your internet speed before you, you know, start a Zoom call or something like that, unless you're going in there to see is something wrong. You know, so if I do speed test, this is another thing you might try. There's a couple of different sites. You can use Google's here. You can do speedtest.net. So speed test transfers something like a 40 megabytes of data. So if I run speed test here, it's going to give me an idea of what my network I'm currently on is capable of. Okay, so I'm on Concordia's network right now. I'm on their Wi-Fi network. And I'm getting 136 megabits per second down, and it looks like 85 megabits per second up. All right, so, and that's connecting to a server in Chicago. So if we want to see some of the numbers we've looked at before, my latency is 20 milliseconds. Okay, so that's the turnaround time when I hit the server in Chicago and the signal comes back. So pretty, relatively quick. I'm hitting something in Chicago, so regionally this is relatively close. Although a couple classes ago we talked about how the internet is kind of like how air traffic works, where I didn't necessarily go directly to Chicago. In this case, we probably did, but there's always a chance that my connection went to Washington D.C. first and then bounced back towards Chicago, something like that. It tries to give me an idea of what very fast means. I mean, from a normal consumer perspective, we would call this good internet, but not necessarily amazing internet. So when they say very fast, they're really telling me what can my internet handle: multiple devices, streaming high definition videos, video conferencing, and gaming, again, at the same time. So we talked about, why do we need fast internet connections? We want them so that we can do many different internet-based applications at the same time. Now, just out of curiosity, let's do speedtest.net. Let's try their connection. Okay, it looks like it's probably going to pump up to a pretty similar number. So yeah, it's 10 less, but that doesn't really matter. It still gives us but interesting enough, look at the ping. So the ping here is 3 milliseconds, way lower. And why is that? What are we connecting to? We're connecting to a server in Milwaukee instead of Chicago. So we're connecting to something much closer to us. Also notice the upload speed here. We talked about synchronous internet connections where versus asynchronous, where most consumer-based internet has a faster download speed than an upload speed. Well, don't worry about whether this is faster or not. It's pretty clear here that our upload speed isn't pointedly slower than our download speed. So what we have here is a synchronous internet connection, which would typically be sold to the public as commercial or business internet. And that's why business internet is more expensive. It has more of a guaranteed uptime. It has two-way communication, so because businesses might run a server, things like that. But it is interesting to see what my millisecond was. It's not that speed test is reading my internet as faster internet. It's that the server they're using for testing is a slower, or is closer to me. I can go here and force a change in server. Here, let's see if I can get something in like Texas. Actually, let's see if I can get something in London. All right, so now we're going to hop the pond. So I'm going to test my internet speed across the internet, or across the continents. right off the bat here, notice what happened to my ping. And my ping quadrupled from what it was to Chicago, and it went up a whole bunch of times what it was to Milwaukee. Notice how much slower the download was. That doesn't necessarily mean anything major, but we were moving a file from 40, let's call it a 40 megabyte file, from London to my local connection. So that means that data needed to flow through multiple hops, multiple servers, each one taking some amount of time as the data flew into that server and then was handed off to the next guy. So we saw our data move way down. Now, upload was still pretty fast. Part of that is because that channel to upload to that server was significantly more open, because probably these places are not receiving a whole bunch of upload requests at the same time. And because most of the use of the internet is download traffic, upload traffic is less congested, even if the bandwidth allotted to it might commonly be yes. So just kind of interesting, interesting stuff here. Let's see if I can get something in Australia. There's Brisbane, Australia. It should be even a higher ping, I would expect. Yep, so 220 milliseconds. So now we're seeing the traveling across the internet and what it does to us. And you're seeing the slowdown in the download. Upload, I suspect, will still be decent, probably faster than this. And realistically, with both of the last two connections, we probably did a little space travel. We probably jumped up to a satellite and had a microwave-based network handing us off across the pond, rather than traveling along a wire under the ocean or something like that. So just kind of an interesting thing of seeing the internet in action and kind of testing that stuff. And I kind of find that here, one last thing. Let's go to Hyderabad. All right, so let's see, for a lot of you, I know Hyderabad is home, or at least in the same country, but several of you are from Hyderabad. I'm going to guess this is faster than Australia, but slower than, oh, it was actually slower than Australia. Yeah, very interesting to sit there and play with a tool like this and kind of see the how the internet actually works. Okay, so enough playing there. That was kind of fun. So that probably didn't have any QoS involved. And a lot of times, if you call up your internet service provider, let's say you're having bad internet, they have you connect to a speed test that's directly related to them, or at least it's not uncommon for them to do that. So if I have Spectrum internet at home and I call up and say, hey, something's not right with my with my connection, they might have me go to, and they especially do this from a consumer perspective. So let's say my internet is having problems and they've debugged it and got it back running. They might say, okay, well, let's go do a speed test. And they have me go to Spectrum's speed test, Spectrum's network for speed test, because that's going to give me the maximum speed. Because effectively, I'm talking to a computer that's on my very large local area network, let's say. I'm not actually having to go through very many hops. I'm going through like one hop to get to that. I'm probably going to get the fastest speed. My guess is, based on past experience here, if I go to Spectrum speed test, This is probably going to be extra fast here because I believe that, oh, it looks like they might use speedtest.net actually. So this is not going to give me a different thing. Historically, they would have run this off their own thing. But one thing I've noticed here on campus, I'm about 10 minutes from my house and I have Spectrum internet at home, but I noticed that I have a very, very quick communication with my network at home. And where I recognize that is I do a lot of virtual reality stuff. And okay, so this is going to Spectrum in Allendale, Michigan. Let's just see what it is. I actually expect it to be slower than some of the other things. So at my house, I do wireless virtual reality. So I have a big, expensive computer in my basement that is, very capable, has a super high-end graphics card in it, lots of RAM, gaming processing power, all this stuff. Now I have a virtual reality headset connected to that computer, but I rarely go down and use it. It's a wired headset. It's, it's what's considered to be a good headset. It's a Valve Index. But I do a lot of VR at my house, but I primarily do it in my living room while seated. So I have my VR headset, my Quest 2, sitting right next to my my chair in my living room. And commonly I'll put, so this is a Quest 2. I don't know how much it's getting blurred out of the video signal here. But whatever, that's a Quest 2. And that cable's just charging it right now. So I have one over at the office as well. But the Quest 2 is a standalone virtual reality headset. So it's made for completely mobile VR, but that's using the graphics processor and everything like that inside of that headset. Now I do that sometimes, depending on what application I'm using, but I play, I might play some games or something like that that would be either they're only available on PC VR or the PC VR version of them would have higher quality graphics and that kind of stuff. And I might prefer that. But I also don't want to go down to my basement and use my VR headset there. I'd rather just use my VR headset from my living room and have it connect to that machine in the basement. So there's a couple of different products out there. The first one that supported it was something called Virtual Desktop that allowed you to play virtual reality games over your local area network as if you were connected to it. And it's shockingly good. I'm sure there is a network performance degrade because just like we're talking about here, there's the ping going from my wireless network to that computer down in my basement. Going to be pretty short ping, but there is it's greater than 0. Then there's also going to be the speed degradation of the wireless network in my house. Maybe some consistency issues. Wired internet, wired network is going to probably be more consistent than a wireless network, since wireless is going to be fighting with a lot of other radio signals and other things that might cause noise, walls and things like that in the house. But ultimately, I would say my end user experience is I'm basically doing VR in my living room wirelessly, connected to my VR machine in my basement as if I was sitting in front of the VR machine in my basement. I would call it pretty close to equivalent. I would say it would be difficult for me to detect the difference between it. So that's all cool and fine at my house. But what I've noticed is if I put this headset on right here and I use my virtual desktop, I can launch a game from my house, play it here in the office, and it still works pretty well. I'm not like at a drastic disadvantage. I can play those VR games. Now, if I'm playing something that is competitive, where there's other people on the screen and that ping rate, because I'm sure the ping does go down when I connect to the machine in my house from here, from the office, the ping probably goes down, but it's still fast enough for, me playing a single player thing, and it would probably be fast enough for me playing a multiplayer thing as well, just because I'm not as demanding of real-time speed and things like that. I probably wouldn't personally notice. It certainly wouldn't be slow. It just might be too slow for like a professional gamer or something like that. But the bandwidth for streaming the graphics and stuff like that is enough. So I can play wireless PC VR in my office off of the computer that's sitting in the basement of my house, because I happen to be on it's seemingly a very closely connected network. So whoever Concordia uses for their bandwidth seems to be similar to who Spectrum uses, or they do use Spectrum. If Spectrum tends to be the source, I'm not sure. But anyways, kind of a interesting thing that kind of reinforces this idea. But we have an overarching concept from any sort of network manager person, where we have various pieces of software that allows us to detect data and throttle it if it's considered a lower priority. And this actually involves, we're going to say modernly, involves artificial intelligence to flag data to be throttled. So part of this is kind of this cat and mouse game where let's take something like BitTorrent, where the initially in the early days of BitTorrent, it was very, very obvious when network bandwidth was being used with the BitTorrent application. As BitTorrent matured, what would end up happening is the data, because BitTorrent was being throttled and other applications similar to that would be getting throttled, the people who are writing those clients, like the BitTorrent client, they would purposely try to make the data look like something else. A lot of times they would make it look like web, HTTP data, which typically would not get throttled. So even though you're downloading a whole bunch of stuff, the software that you're using as the consumer is trying to make your data masquerade as just web data, and therefore it would kind of bypass the QoS stuff and not slow down. So it was this game of trying to having the consumers, the let's call it the more hacker type consumers fight against the network managers who were trying to keep the quality of their overall network at a reasonable level. So now our newer pieces of software for QoS use machine learning based artificial intelligence to analyze data and not just look at the protocol the data is operating over. Historically, they would have looked at just HTTP if we're talking about web. So as long as something like BitTorrent started using HTTP, the QoS, the early day QoS software packages would just say, oh, that's web traffic, leave it alone. Even though it wasn't really web traffic, it just looked like web traffic. So now modern day QoS doesn't just rely on what it looks like, it actually passes it through a model, a machine learning model that tries to classify the data as its actual type of data. What is this really? Not what does it look like, but under the hood, what is it really? All right. So you can kind of think about this in terms of real life. If you are, at a Halloween party and everybody there is in costume, depending on how good their costume is, you might be able to recognize the actual person who's wearing the costume, even though they're trying to dress as someone else. All right, because you're a human being, you're intelligent, so you're using your memory, your facial recognition, your body type recognition, all those things. If we're at a Halloween party and I'm in a costume, you know, you guys are going to probably be able to zero in on me relatively quickly because I'm probably one of the bigger guys in the room. I know some of you haven't met me in person yet, but I'm a pretty large human being. I'm, you know, 6'5", you know, 390 pounds. I'm just a big guy. So chances are I'm going to be the biggest guy in the room. So you can narrow it down where Lippman might be. It's kind of the point. But if you got a whole bunch of average size folks in a room, I think I told you when I was in India, the wrestling's pretty big there. A bunch of folks were coming up and taking pictures with me. They thought I was Big Show from wrestling. It's kind of a funny thing. Was signing autographs and stuff. All right, but it's kind of a similar type model to that, where human beings, we already have facial recognition type models, you know, in our brains. We're able to recognize people that we've seen before, somehow magically. So we have pattern recognition stuff in our brains. And if we were at a Halloween party, we would probably be able to do a pretty good job of detecting, okay, that's Nancy from accounting or something like that. Well, so our modern day QoS systems are doing something very similar. They have been trained up by looking at BitTorrent data. For example, I just keep using BitTorrent as an example just because it's a common example. I don't want to portray it as that's the one bad guy on the internet, because there's plenty of good uses for BitTorrent technology. But in any case, what they trained those neural network models up on is they looked at a whole bunch of data that was known to be BitTorrent data. And then they started feeding it data that, okay, this is BitTorrent, this is something else. This is BitTorrent, this is something else. And trained up that model so that it could correctly identify the data, the pattern of the data, regardless of which protocol it was using. Because a lot of times machine learning based things, they are doing data, they aren't approaching it logically. It's kind of a fascinating thing. When you have the AI class, we'll see who ends up teaching it. If it's face-to-face, I'm hoping it would be Professor Josh Locklear, but it's always a chance it'll be me. I do a lot of the face-to-face classes. But my first experience with AI when I was an undergrad was pretty fascinating. We wrote our own. I mean, now there's tools for just generating a neural network. So you probably wouldn't write a neural network from scratch anymore. But you know, in my class, we wrote a neural network from scratch, and we decided, okay, we're gonna do multiplication tables, like flashcards. So what we did is we fed the neural network the 1s through 5s multiplication table. You know, 1 times 1 is 1, 1 times 2 is 2, so on and so forth. And so when you first start doing it, the neural network is just making a guess. You're putting in data, and it's spitting out a number, and that number is either right or wrong. And chances are, early on, they were all going to be wrong. So using an algorithm we were looking at was called back propagation. We were making a little adjustment, kind of, you know, the neural network's just a whole bunch of little neuron objects in code that are connected to each other through just a number. Here's a weight for this, how strong is the connection between these two neurons. We're just modeling how we think a brain works. All right. So the idea is we kept tuning this model over and over and over again until it started getting correct answers out here. And once we did that long enough, all of a sudden it was getting 100% accuracy on the entire 1 through 5's multiplication table. We balanced it just right, that it didn't matter which two numbers I fed in as inputs. It gave me the correct answer on the output. I got it just balanced right. So now, but what was fascinating is then we fed that model, that trained model, we fed it the 6 through 10's multiplication table. This is data it had never seen before. And it got like 94% of them right. So it was fascinating that I didn't I didn't teach, we can write code that does math accurately. So we didn't teach this neural network to do math. We had it stumble upon the pattern of multiplication. And it just blew my mind that the accuracy that I effectively created a guesser at multiplication answers, and it was getting it right. Because under the hood, even though we have a logical approach to how we do math, there is an underlying pattern to mathematics that does exist, but it's not something that human beings, that's not how we conceptualize math. But based on that neural network, that's kind of proof that it does exist at some level. So just kind of fascinating thing. So that's a similar thing that would be happening here, where they've trained up a model that looks at data that's, where we know the answer. We know this is BitTorrent data or this isn't BitTorrent data, for example. So they trained it up. So now our quality of service applications, when data comes in, it's just passed through these either various models that know how to detect problematic data, and anything that it flags as, yes, this is problematic, it throttles. Now, sometimes you might get some false positives. It's possible that will happen, but the hope is that more often you are flagging data that is problematic. That maybe was trying to look like benign data, trying to look like web data when it was actually something else. So kind of an interesting thing how our QoS stuff has evolved over time. All right, so any questions about QoS and kind of the role it plays in our internet end user experience? Okay. So what we'll do is kind of next time, I think next week is is it our last week? Or is it the second to last week? I have to double check. But in any case, what I want to talk about primarily next week is the HTTP protocol, kind of how that communication with web servers actually works. The idea of MIME types, APIs, and the concept of RESTful APIs. So I think that should probably, by the time the class is over, we should have a pretty good bead on how the network that we all use on a day-to-day basis actually works. And then you guys will have the more theoretical knowledge you've gotten from the coursework. So hopefully those of you who have not had undergraduate classes in computer networking will be relatively caught up and will no longer just be your average consumer knowledge person. Okay, so let's go ahead and call it quits for today. The next assignment is up on Blackboard. Questions, comments, concerns, bribes? All right, I will see everybody on Monday.
Sure, Dr. Thank you.
Yep, have a good one.